All right, so it's my great pleasure to introduce Raj to begin the afternoon's thesis presentations. Raj will be telling us about his work this year in basis reduction and lattice cryptography. I'm also delighted to inform you that Raj is already employed following his imminent graduation. He'll be going to Madison, Wisconsin to work for Epic Systems. So please enjoy.
Thanks for coming to my talk. I'm going to be talking about basis reduction in lattice cryptography, as Nora already mentioned. Let's see if this works.
It does not.
It does not?
As far as I can
Okay.
tell.
So let's just use this. So first of all, before getting to lattice cryptography, what exactly is cryptography? It's something that stems from the desire to secure private information from unwanted eavesdroppers. So say I want to send Rob over there a secret message and I don't want anyone else eavesdropping. I use some mathematical algorithms to ensure that no one else knows what we are talking about. And it's a very pressing issue today. You want to secure your information against a lot of other eavesdroppers, maybe the government, maybe some data mining entities like Facebook or Google or what have you. But this need has been present for centuries actually. And one of the original cryptographic algorithms was the Caesar cipher. So say Julius Caesar wants to send a secret message to his troops on the battlefield, and he doesn't want his enemies to know what he's talking about. Well, he'll use some sort of mathematical key to change this plain text message into this ciphertext. So what his troops see is this message over here, and also his enemies also see this message. And his enemies don't know what he's talking about because they don't have the key, but his troops do. So the key over here is just a shift of 5. So you map A to F, I believe, and so over here E goes to J, N goes to S, and so forth. To decipher the message, you apply the inverse of that key, so you subtract by 5. Where is cryptography today? Two of the most famous cryptographic problems are the integer factorization problem and the discrete logarithm problem. Integer factorization, taking the integer, finding its prime factors. Discrete logarithm, given a base b and a number a, finding the exponent that b is raised to get the number a. Those are two very difficult mathematical problems, and RSA and AES are all based on these mathematical problems. And with classical computing, these are actually very, very difficult, given a high enough dimension and high enough integers. But today, we always hear about quantum computing. What is quantum computing? Well, to keep it simple, it's just something that uses quantum physics to make computing much, much faster. That's like not even comparable to what we have today. So much faster than classical computers. Some algorithms that can be run on quantum computers are Shor's algorithm and Grover's algorithm. Shor's algorithm solves the integer factorization problem pretty quickly. Grover's algorithm is kind of like an intelligent brute forcing of this discrete logarithm problem. So RSA, AES, any of those crypto systems on elliptic curves also, those are not really secure. However, quantum computing is still very much in its infancy. They're not really publicly available or even available to large industries. I read that as of 2014, the largest integer that a quantum computer could factor was 143, which is nothing in terms of cryptography. It's very, very small. So it's still a long ways away, but we should always have the motivation to make existing cryptography even stronger, because cryptography has always been a race between code makers and code breakers. So on the one hand, you want people to have a very secure communication, but that is spurred by code breakers making better and faster algorithms for cracking these codes. So we should assume that quantum computers are already existent, and we should devise cryptographic systems based on that assumption. I didn't know it's going to cut off there. Hopefully that's not a problem. But why study lattices? So quantum cryptography is a very large umbrella of fields, and lattices are probably the most studied in that umbrella. So that's one reason why to study lattices. They're quantum resistant. Another is that they're just very beautiful mathematical objects to look at. They're at this neat intersection of linear algebra, number theory, geometry, even topology, if you get even deeper. So it just combines a lot of different mathematical knowledge, and they're just, they make these nice patterns when you display them, This is a very basic lattice over here in 2 dimensions. So yeah, that's why I picked lattices. My goals with this thesis were to understand code breaking around lattices, not code making, but code breaking, which is also called cryptanalysis, and also to condense and simplify the existing literature. When it comes to cryptography, lattice cryptography, there's all these different papers all over the place. Some are from the very early 1800s, which is when lattices were first studied by Gauss and Lagrange, but it became much more sophisticated in the 70s, 80s, 90s, and the 2000s. So there are all these different papers. I want to condense and simplify them so that anyone who's studied linear algebra should be able to understand what's going on. Just to make it accessible, and also some of these papers are very computer science heavy, so just to make it more mathematical as well. So first we're going to begin with a study of a classical crypto system, which originally was not based on lattices, and then we're going to connect it to lattices later on. So that classical crypto system is something you may have heard of already. It's called a knapsack crypto system, and they're based on this very difficult mathematical problem called the subset sum problem. So the definition of the subset sum problem is if you're given a set of weights W, where your dimension is n, and some value s in the integers, the subset sum problem is to find a subset of these weights such that their sum equals exactly s. So to think about it intuitively, say you have a bag or a knapsack, as it's called, with capacity s, and you have a collection of objects that each have size w, or wi. You want to find the subset of those objects that exactly fit the capacity of your bag. And this is actually a very difficult problem when it gets to high enough numbers. So classical knapsack crypto system is based on this formula over here. Your set of weights W is public information. Everybody in the world has access to it. And say Bob wants to send a secret message to Alice. So Bob has some plain text, which you will encode first as a binary vector, x, where binary meaning that all these values here are either 1 or 0, corresponding like what your plain text is. And then he will encode that as a sum s, based on these public weights over here. Alice receives the sum s over there, not the original plain text, and she needs to find x to recover the original plain text. And this is actually a very difficult problem to do by just brute forcing. If you just try every single vector that's possible, it's in the order of 2 raised to n, which in the language of computer science is called really bad. It's very, very inefficient. So there is a sort of better way to go about it, but it's still quite brutal. So if you cut the dimension in half and you just look at the indices that go to n-1/2, and then the indices after that, you break it down into these 2 sets, and you look at the sums over this set and the sum over that set, and you subtract the sum over this set from S. You scan the 2 sets for an intersection. You scan the intersection of the 2 sets for an element, and an element arises precisely when there's a solution to the subset sum problem. So you can go, this is like a semi-naive way to do it, but it's still exponential. So this is not really a practical way to go about it. Well, you might be thinking, hey, isn't cryptography based around really difficult mathematical problems? Like, wasn't the point to make sure that an eavesdropper who intercepts the message isn't able to decipher the message? So this is really hard, so that should be a good thing to devise a crypto system around. Well, that's not really the case, because although it's hard for an eavesdropper Eve, it's also equally hard for the intended recipient Alice. So they're both faced with the same exact problem, which is, so basically no one can read the message except for Bob, who sent the message. So you can't really devise a system around this. So what you need is some sort of easier version of the subset sum problem, and some sort of trapdoor information, it's called in cryptography, where Alice has access to some secret information that Eve does not, and that allows Alice to decipher the message and know what's going on. So Merkle and Hellman, you've probably heard these names from computer science, Merkle from Merkle trees and Hellman from Diffie-Hellman. They devised this crypto system based around super increasing sets. So the set of weights that you choose is super increasing. It's not an arbitrary set of weights. So what is a super increasing set? It's a set of positive integers, a0 to ak, where each ai is greater than the sum of all the preceding integers. So the Merkle-Hellman crypto system goes as follows. So Alice is going to choose some public w, Alice is going to choose a super increasing w, starting with the condition that the initial weight is greater than 2 raised to n, and that's just for security purposes. And she chooses two positive co-prime integers, a and b, such that b is greater than the sum of all these weights. Then she computes p, where each pi is a times wi modulo b. And her public key, instead of w this time, is going to be the vector p. And her private key is w, a, and b. So by public and private key, I mean this is public information that's available to everyone in the world. And private key is something that she keeps to herself. And no one in the world, not even Bob, knows what that information is. So for encryption, it's the same thing as before, essentially. Bob has some plain text in English or whatever language, and he converts that to some binary vector x composed of zeros and ones, and then he sends a ciphertext s, not with the dot product of x and w, but with the public key now as p. So he takes the dot product of vector x and p, and sends that over to Alice. So Alice receives that sum, and she has access to the secret integers a and b. So she's able to compute a inverse s, and a inverse s over here, that refers not to 1 over a, but the inverse of a in modular arithmetic. And that allows her to recover this sum, and there's a simple recursive algorithm to find x once you have the sum of xi and wi. So in that way, she's able to recover the plain text. So that is the Merkle-Hellman crypto system, just laying the groundwork there, and we're going to come back to that near the end of the talk. But first, I'm going to talk about what I really studied this year, which is lattices. So what are lattices? There are two different definitions. They're both equivalent. Take whichever one based on what field of math you like. The first one is linear algebra. It's given a set, basically given a basis of linearly independent vectors, b0 to bn minus 1. You take all the integer linear combinations of that set, and that's your lattice. Otherwise, if you prefer geometry, it's basically a discrete additive subgroup of Rn. And by discrete, I mean basically there's a space between each point in your lattice. It's not continuous. So here's a simple example of a lattice. You're given the basis 3, 0, and 2, 4. And that's these two vectors over here. Is basically all the integer linear combinations. So all of these are lattice points or lattice vectors over here. An important property is called the minimum distance of a lattice, and that's defined to be the infimum of all the norms of the non-zero vectors in your lattice. And if you don't know what an infimum is, because that's not a requirement for linear algebra, you can basically prove that this infimum you can replace with minimum, and that's basically this theorem over here. For any lattice, there exists a lattice vector that achieves this minimum distance. So that's pretty nice. And a lot of the hard cryptographic problems around lattices are based around this property, which we'll see in a few minutes. Another important property, I really hate that this is being cut off, is the fundamental domain. So for any basis B, we define the fundamental domain or the fundamental parallel pipet to be the set of all the sums of the basis vectors, all the linear combinations where the coefficients are from 0 inclusive to 1 not inclusive. So just picture the lattice we had before. I'm using the same exact example over here. These are your basis vectors. The fundamental domain is basically going to be this shaded region over here, including the two basis vectors, but not including the other two boundaries of your region. So these two boundaries are not included, and these two are. And the fundamental domain has a nice, the volume of the fundamental domain has a nice relation to the orthogonality of a basis. So for any lattice L, the Hadamard inequality states that the volume of the fundamental domain, and volume is as in the measure theoretic sense, basically like the area in 2 dimensions, is bounded above by the product of the Euclidean norms of all your basis vectors. And we use the term Hadamard ratio to refer to this divided by that. And this actually is a good measure of the orthogonality of a basis. So the closer it is to 1, the more orthogonal your basis is. The farther away means it's less orthogonal. And it equals 1 exactly when your basis is perfectly orthogonal. And that's a very desirable property for a basis, to be orthogonal. So the fundamental domain, you can probably see from the picture itself that I had before, it basically gives you a tiling of Rn, where if you have any random real vector, there is a unique pair of 1 fundamental domain vector and 1 lattice vector that's going to, and the sum of those 2 vectors is going to give you exactly your real vector. And as I alluded to before, the 2 hard cryptographic problems in lattices are based on the minimum distance. So the first one is the closest vector problem. So given any lattice L and some real vector W, the closest vector problem is to find some lattice vector that minimizes the distance V minus W. So the distance between the lattice vector and the given vector should be minimized. So if you are given this real vector over here in red, you want to find the closest lattice vector, which is this blue vector. And another hard problem is the shortest vector problem, where you want to find the shortest vector in the shortest non-zero vector in your lattice. So you can actually see that this is basically the closest vector problem for the 0 vector. You want to find the closest non-zero lattice vector, so that's going to be the closest vector to 0. And in this example that we have, it's 3, 0 and negative 3, 0. They have the same Euclidean norm. And if you've taken group theory, you know that the 0 vector should be an element of the lattice because the identity element needs to be an element of the lattice because it's an additive subgroup of Rn. So that's how you can transform the shortest vector problem into the closest vector problem just for the 0 vector. Well, if you study linear algebra, you can know that you can generate the same vector space with different bases. So you can actually do that with lattices as well because lattices are vector spaces. So over here you have the same exact lattice but generated by 2 different bases. So over here is 3, 0, 2, 4, the same example we've been working with, and over here you can't see it, but it's 11, 4, 19, 8. These weird looking vectors over here. And think about solving the shortest vector problem in this scenario and in this scenario. Over here you're given a basis, and the shortest vector happens to be a vector that's already in your basis. So if you wanted to find the shortest vector, if you're already given a nice basis like this, you just have to scan your basis and look for the shortest vector. It's a pretty easy problem if you just know what's going on. But over here, the shortest vector is nowhere near these basis vectors that you're given. So you actually have to do a bit of math to find out what the shortest vector is. So if you want to devise a good crypto system that can really secure your information, and it's based on the shortest vector problem, you want to use a bad basis. And if you are looking to break this system, then you know that given a lattice, you can find a better basis that generates the same lattice. So if you're given this scenario over here, you want to find the shortest vector, you might consider transforming this basis into that basis and then looking for the shortest vector. So that's a bit of what we're going to explore later on. So one of the first algorithms devised to solve the closest vector problem was due to Babai. He devised it in the 80s. And he uses the idea of fundamental domains to solve the closest vector problem. So the idea is basically, remember that the fundamental domain tiles your real plane. So given any vector, given any real vector, you want to find the unique translate of the fundamental domain that contains that vector, and then find the closest vertex of that fundamental domain to your given vector. And his algorithm formally goes like this. So you're given some real vector W, you compute what it is exactly based on your given basis, and then you basically round each coefficient that you assign to the basis to the nearest integer, and that does the same thing as finding the closest vertex of your of the fundamental domain, and then that's the vector that you return. And we do have an example, but in the interest of time, I'll probably just skip it. But you're given some nice bases over here, 3, 0, 2, 2, 4, and you're given the vector 3, 8. Using Babay's algorithm, you find the closest vector 4, 8. And 4, 8 is pretty close to 3, 8. Yeah, in fact, is the closest vector, so your algorithm works in this case. But now let's look at the bad example, where your given basis is 11, 4, 9, 8. This basis is not anywhere close to orthogonal, right? And the output of the algorithm is actually the vector -7, 4, which is all the way over here, and your given vector is over there. So you see that Babay's algorithm works well in some cases when the basis is near orthogonal, but in other cases when it's not orthogonal, it doesn't work at all. And the idea is because you're using fundamental domains. So if you look at the fundamental domain generated by this, these two basis vectors, it's, you know, the corners are all over the place. Like if you start off over here, the closest lattice vector is going to be this point over here. But if you're looking for the closest vertex of your fundamental domain, that's going to be this point over here. So it's not going to return the ideal vector. So Babay's algorithm is a good start, but it's not enough. We need to deal with a nice basis if we want to crack the closest vector problem and the shortest vector problem. And that's where reduction algorithms come into play. So you want to transform any given basis into some sort of nice basis, and there are different ideas of what constitutes a nice basis. So you do that with some reduction algorithm, and then you take that and then you use Babai to find the closest lattice vector. So let's talk about some reduction algorithms. So for any linear algebra student, you're very familiar with this process, the Graham-Schmidt process. It can be very tedious to do, but you know, we all love it. So given any basis, you so you loop through the entire basis, and you look at the index I. You reduce I based on some multiple of the preceding vectors, preceding basis vectors. So you might be thinking, okay, we have this handy algorithm that's taught in linear algebra. Why is that not enough? Why do you have this entire field of lattice cryptography if you already have a perfectly working reduction algorithm? Well, the problem is lattices are discrete subgroups, as we talked about. They are in Z, they're not in R. So the Graham-Schmidt algorithm is actually going to return a basis that is in Rn, not in Zn. And that's not something that we're looking for. So we need to find a reduction algorithm that returns integers, not just any real number. So the first attempt at this was back in the early 1800s by both Gauss and Lagrange. It's usually attributed to Gauss, although Lagrange discovered it before Gauss did. Reduction in 2 dimensions. We call a basis B in R2 Lagrange reduced if it satisfies these following conditions, where the first vector is shorter or is no longer than the second vector. And if this is basically looking at the projection of B1 onto B0, that is bounded above by 1/2. So why is a Lagrange reduced basis desirable? As we can see, B0 is shorter than B1. Well, actually, B0 is going to be a shortest vector of your lattice. So if we have a given 2-dimensional lattice, if we apply Lagrange reduction, then we actually solve the shortest vector problem. So Lagrange's algorithm was as follows. He had 2 basic steps. One is a swap step, and one is a reduction step. Reduction is basically to decrease the length of your basis vectors so that you can get the shortest vector at the output of the algorithm. And the swap step is to reorder your basis vectors. So say B0 is actually longer than B1. That's not what you want, because you want B0 to be the shortest vector of your lattice. You just swap them. So that's your first step over here. You swap B0 and B1 if the order is messed up. And then over here, you reduce each vector by by a multiple of the preceding vector. And in that way, you get a nice basis. And we have an example here. Again, I won't go through all the steps, but if you're given this example of 11.4.19.8, you apply some reductions and some swaps. I had a pretty good diagram over here, but what's going on is you have this basis of vector 19.8. You subtract it by multiples of this other basis vector, that's 11.4, and you get another basis vector here that's -3.0. So -3.0 is much shorter, much nicer to look at than 19.8.
But Raj, the notation you're using, the sort of half floor and half ceiling, what does it mean?
Rounding to the nearest integer.
Nearest.
Yes. Yeah. And you go from 11.4.19.8 to -3.0, -1.4, which is a much nicer basis, much shorter, much more orthogonal as well. So that's nice in 2 dimensions, but no good crypto system is going to be based around problems in 2 dimensions. That's just very easy to deal with. So you want to look at higher dimensions. So you want to find an analog for the Lagrange reduction algorithm in not just 3 dimensions, but very, very high n-dimensional space. But it's very hard to do that. It's very hard to come up with a perfect analog because you're given all these basis vectors, b0, b1, b2, all the way to some bk. If you want to reorder bk, say that this is actually shorter than the preceding vectors, you need to compare bk with bk minus 1, with bk minus 2, with bk minus 3. Say you reorder, and now the new bk is maybe shorter than the next bk plus 1, so, or is maybe longer than the next bk plus 1, so you need to reorder that, and there's just a lot of moving parts going on. So it's hard to find a perfect analog, but Lencha and Lovas in 1982 came up with a good stab at the problem. So they developed an algorithm that was actually made to factor polynomials over the rationals, but it ended up having a number of applications in combinatorics and number theory. One of them is approximating the minimal polynomial of an algebraic number, and another one is integer programming with a fixed number of variables. But the application that we're concerned with is basis reduction for lattices. So Lencha Lovas, we abbreviate that to LLL. So what is an LLL reduced basis? So we pick some value delta that's between 1/4 and 1, including 1/4 and not including 1, and we'll talk about why later on. A basis B is delta LLL reduced if it satisfies the following conditions. The first condition is called a Lovas condition. The second is, again, for swapping, or sorry, for reduction. So over here, we consider the Gram-Schmidt vector, bi minus 1. You consider the Euclidean norm without squared times delta. It's bounded above by this condition over here. And that's, I won't go through exactly what that is, but that gives you a nice ordering of your basis. An equivalent form of the Lovas condition, which they actually use in their algorithm, is as follows. This is your delta value over here, 3/4. We usually use 3/4, and that's what they used in the paper. And it's just a nice value to have. We'll talk about why we can't use some other values later on. So this is an equivalent way of stating the Lovas condition, and it follows from that condition that this is true, that the Gram-Schmidt vector bi, take the Euclidean norm squared, is greater than 1/2 times the Euclidean norm squared of the Gram-Schmidt vector bi minus 1. So essentially what you're doing is that, in the words of Ott and Regev, each vector is not much shorter than the preceding vector. That's a desired property. Okay, so how does LLL reduction actually help? Well, if you LLL reduce a basis and you look at the length of the shortest vector, it's actually bounded above by this factor of the minimum distance. So the length of B0 is bounded above by 2 raised to n minus 1 over 2 times the Euclidean norm of V for any lattice vector V. So this isn't actually solving the shortest vector problem, but it's giving a good approximation. And you find that in cryptography, that's often what we're doing. We can't find exact solutions, but an approximate solution is good enough to render a crypto system obsolete. So let's dive into the LL algorithm, and it has a few moving parts. And in the interest of time, I'm going to rush through the next example I have, and I apologize for that. But I'll try to do the best I can. The three moving parts we have are B, the basis that we're actually reducing, B star, which is the Gram-Schmidt basis, and K, which we call the working index. And that's the current, so BK will be the current vector that we're looking at. We call that the working vector. And then we loop through our basis and we change our working vector to the next basis vector. So there's two major steps, and it's the same as the Lagrange reduction algorithm. You have the reduction step, which is reducing the working vector by multiples of the preceding vectors. And then you have the swap step, which is swapping based on whether the Lobos condition is met. And that gives you sort of an approximate ordering of your basis. This is the LL algorithm defined over here. So first you compute your Gram-Schmidt basis, and you're going to keep track of that throughout the algorithm. And you initialize your working index to 1. Then you loop while k is less than or equal to n minus 1. And then you have a nested loop, which goes from k minus 1 all the way to 0. So you take your working vector bk, and you reduce it by multiples of first bk minus 1, because j is k minus 1. Then you reduce that by a multiple of bk minus 2. Then you reduce it by a multiple of bk minus 3 all the way to 0. And at the end, you need to recompute your Gram-Schmidt basis because it's been updated. Yeah.
Can you guys quickly remind what this asterisk means?
Yeah, so that's the Gram-Schmidt basis over here. So I refer to the Gram-Schmidt basis as B star. So Bj star will be the jth Gram-Schmidt vector. And then you check the Lobos condition. So you've done your reduction here, then you check the Lobos condition. If the Lobos condition is passed, that means it's reasonably well ordered, so you can move on to the next basis vector. So you increment your k to k plus 1. If the Lobos condition is not met, you need to swap it to make sure that it is somewhat reasonably ordered. So you swap bk and bk minus 1, and then you possibly decrement your k. You set it to the max of k minus 1 and 1. So you can see that because you have all these vectors, your working index k is going to move up and down based on how your ordering is at that given time. And if you guys want, I do have, I think it's a working implementation of the algorithm. It's open source on GitHub. You guys are welcome to play around with it and make contributions if you want at github.com/r/kane/LLL. And it works pretty nicely. You enter your basis. It gives you all the steps. You can look at the steps if you want or not. You can just skip all the way to the end. So I think we have time for an example. How long has it been? 35.
You have like 6 minutes left.
So maybe not time for an example, but I do discuss this in my paper, which you guys can look at. I'll just show you the input and the output. So you're given some nasty looking basis, 111, negative 102, 356. You apply the reductions and the swaps, and what you end up with is 010, 101, negative 102, which, compare these two sets of bases over here, that one is much more orthogonal, much shorter, much nicer to deal with. And if you think back to the Hadamard ratio, which I introduced earlier, this is actually more orthogonal by a factor greater than 10, so actually much more desirable. So that's just the power of the LL algorithm when you're dealing with 3 dimensions and with very short vectors. But in higher dimensions, it's actually a much more pronounced effect. So you might be thinking, does the algorithm actually terminate? Because as I said, the working vector, the working index goes up, goes down, but does it actually break out of this? Does it actually reach n so that you can break out of the loop? Well, they actually prove this in the initial paper, where if you let omega be greater than the maximum of any of the basis vector norms squared, the number of arithmetic operations needed by the LL algorithm is in the order of n raised to 4 log omega. So the algorithm does terminate, and n raised to 4 log, that's pretty useful actually. That's polynomial time. So this is a pretty useful algorithm. So let's talk about delta, and this is a very important number over here. So we typically use delta equals 0.75 just for convenience, and that allows it to run in polynomial time. the closer you get to 1, the more orthogonal your basis is going to be. But then why don't we actually use delta equals 1 if we want the most orthogonal basis? It's actually, that's where you have like mathematics versus computer science. Like this is optimal, but it's not practical. Delta equals 1 is called the optimal LL algorithm, but it actually doesn't run in polynomial time because the Laval's condition becomes harder and harder to meet as you increase your value of delta. So as you when you have delta equals 1, it's actually unclear if your algorithm is ever going to break out of that main K loop. So there are attempts to see if you can make the optimal LL algorithm actually practical. In 2003, Colby showed a linear bound for the number of iterations of the optimal algorithm, but you don't know how much time is actually required by each iteration. Because to show that your algorithm runs in polynomial time, you have to have a linear bound for the number of iterations, and then each iteration has to take some finite time. So that second component has not been proved yet. So we talked about the LL algorithm. Now it's time to bringing it all back home, as Bob Dylan put it. Let's go back to knapsacks and discuss how we can connect lattices to the Merkle-Hellman knapsack crypto system. To recall how this works again, Bob sends the dot product of X, which is his message, or his plain text, with the public key P. Alice receives that S. She has the public key P and the private key WAB. And let's say now that Eve intercepts this message. Oh no. Now, what is she going to do? Before we saw that the brute force algorithm is in some exponential order. So that seemed like it was going to be secure. We can secure our messages against Eve. But now Eve has studied lattice cryptography. She knows the LL algorithm, so she's much smarter. Now she can actually crack this code. So let's see what she does. She knows the public vector P, and she knows the sum S. That's what she intercepted. So she forms a basis n+1 by n+1, like so, where you have this first row, which is 1, and then all zeros, and then P0, then 0, 1, all zeros, and P1, all the way over here. That's n-dimensional. And then you have zeros all the way till negative S. Then she takes the rows of that matrix as basis vectors for her new lattice. This is going to be an n+1 dimensional lattice. She computes, so I forgot to put this in the slide, but she is going to compute, she's going to want to retrieve this vector, big X, which is the sum of all the basis vectors multiplied by xi minus bn, which is your last basis vector there, all zeros till negative S. And that vector, because of how the P's and S's are related, is actually going to be your vector X appended with a 0 at the end. So if you're able to find this vector big X, and you know you just need to chop off the 0 at the end, that's pretty easy to do. And your vector big X is actually quite short because, remember, X is binary. So these are all zeros and ones, and then a 0 at the end. So we need to find a short vector in a lattice. And what does Eve know? She knows lattice cryptography now. She knows the LL algorithm. So she can apply the LL algorithm to find that vector, big X, which is a quite short vector. And I won't go through exactly how this works, but Lagarius and Odlisco have shown that there's a very, very high probability that the LL algorithm actually finds this vector, big X. And there's a very high probability that the first vector in that return basis is, in fact, the shortest vector of this lattice. So the LL algorithm works pretty well. And this is an example, which I won't go through all the way. But if you have this scenario over here, if that's the weights that Alice selects, and she goes through the Merkle-Hellman crypto system, Eve is actually able to compute the LL reduced basis, and the seventh basis vector is this over here, which is the original message if you just chop off 0. So Eve is easily able to retrieve the original message plaintext, and she is able to crack this crypto system. So the knapsack crypto system was believed to be very desirable because it runs very, very fast, faster than RSA, and that's why it was used so heavily in the 80s. But then this algorithm, or this approach, was developed by Shor and he showed that the knapsack crypto system doesn't actually work. It's not desirable, so it was kaput after that. So that's basically what I studied in my thesis. There are many other directions I could have gone. In lattice cryptography itself, if you want to look at code making side instead of the code breaking side as I looked at, you can look at some of these crypto systems, GGH or ntrue. GGH was actually broken in the late 90s or the early 2000s, but it's still pretty nice to study. Ntrue is actually not known to be broken by any lattice cryptanalytic methods. So right now it's the leading candidate for a lattice crypto system. And it's also open source, it's on GitHub, so you guys can check it out. There's a nice discussion that they have in the source code about how it actually works. Other quantum resistant cryptography, I could have also studied supersingular elliptic curves or hash-based cryptography, but lattices, there's just the most literature on that field of lattice cryptography, so that's what I studied. And I want to thank a number of people for this. First, all my mathematical friends and also non-mathematical friends for helping me throughout this journey. I especially want to thank Nora, and without her patience and advice, this would not have been possible at all. Leo for reading my paper, all the professors for helping me. Also, I want to thank Professor David Crum for nurturing my interest in cryptography and for pointing me towards lattice cryptography. And thank you all for coming to this talk.